Dear students, welcome to another DSP Lab session. In today's lab, we'll implement circular convolution in the Octave environment and then verify the convolution properties. For implementing circular convolution in the Octave environment, we'll be writing two programs. In the first program, we'll use concentric circle method or the direct method that we have studied in the theory classes to obtain the circular convolution between two sequences. And in the second program, we'll implement circular convolution by using DFT and IDFT method. And later, we'll verify commutative property, associative property, and distributive property of the convolution. Before we go into programming, let us revisit the circular convolution. Now, we know that convolution between two time domain sequences will lead into multiplication of their spectrum in the frequency domain. So to obtain the circular convolution, now circular convolution is the time domain aliased version of the linear convolution. We have been studying that in our theory classes. Now just for the implementation sake, let us consider two 4-point discrete time sequences. x1 of n 2121 and x2 of n 1234. And for these two sequences, circular convolution x3 of m is defined as summation n equals to 0 to n minus 1 x1 of n multiplied by x2 of m minus n of capital N. Now x2 of m minus n of capital N is due to circular symmetry. Now both of these sequences will be represented on the circumference of the circle. Normal direction of plotting will be in the anti-clockwise direction or the counterclockwise direction. So x1 of n will be plotted in the anti-clockwise direction. x2, n is the independent variable. For the first iteration for m equals to 0, this will be x2 of minus n. Now x2 of minus n is the circularly folded version of x2 of n. Now to obtain the circular folding, all these sample values of the second sequence will be plotted in the clockwise direction, as you can see on the screen. Now this is the first iteration, we'll come to it, but one of the sequence will be kept as it is, second sequence will be circularly folded and then shifted in the anti-clockwise direction or the counterclockwise direction. So to obtain the first circular convolution point, we'll substitute m equals to 0. So for m equals to 0, we'll rewrite this equation. It will be summation n equals to 0 to 3, because from both the sequences, maximum number of samples in both the sequences is 4. So 4 minus 1, 3. x1 of n, x2 of minus n. Like I said, x1 of n is plotted in the anti-clockwise direction, and x2 of minus n, to obtain the circular folding, will plot it in the clockwise direction. Now this partial product addition mean each samples will be multiplied together and then their partial products will be added together. So x1 of 0 will be multiplied to x2 of 0. Likewise, x1 of 1 will be multiplied to x2 of 3, and so on. So when you multiply two corresponding samples and add the partial products, the first circular convolution result, what you obtain is 14. Now for m equals to 1, the circular convolution formula can be written as x3 of 1 equals to summation n equals to 0 to 3 x1 of n x2 of 1 minus n. Now x2 of 1 minus n mean this circularly folded sequence shifted by one sample in the counterclockwise direction. So in the previous case, x2 of 0 was at the reference point, that is towards the right side. Now it has been moved up by one position. So all these samples will be circularly shifted further. Now again, corresponding samples will be multiplied together and their partial products will be added together. 2 into 2 plus 1 into 1, 2 into 4 plus 1 into 3. So it will result into 16. So this will be the second point in the 4-point circular convolution. And these step will be repeated for m equals to 2 and m equals to 3 to obtain the last two samples of the circular convolution. For m equals to 2, x3 of 2 equals to summation n equals to 0 to 3 x1 of n, x2 of 2 minus n. Now x2 of 2 minus n is 2 unit shift in the counterclockwise direction compared to x2 of minus n circularly folded sequence. So multiply the corresponding samples and add the partial products, will get 14, and the same way we have repeated it for m equals to 3 as well. So the circular convolution between two sequences, circular convolution between the sequence 2121 and 1234 will result into a 4-point circular convolution result with values 14, 16, 14 and 16. So this is the output that we are expecting after executing our program. Now in the first program, we'll try to implement this circular convolution expression as it is. Now to implement this in the Octave environment, we'll be using for loops. We'll be using two for loops because there are two indices here. First index is varying from 0 to n minus 1 over this summation. First index is n. And second index is m, which is also varying from 0 to n minus 1. So we'll be using two for loops to define both of these indices m and n. We have changed the terminology in our program, and then we'll implement the addition of these partial product. Okay, so the first program is by implementing or to implement circular convolution by direct method or the concentric circle method, and it goes like this. CLC clears the command window, clear all, clears if there is any workspace data in the workspace, close all additional graph windows. If they are open, they'll be closed. Now we'll take the two sequences from the user itself. X1 input, enter the first sequence. X2 input, enter the second sequence. And how many point circular convolution has to be computed? Now it will also be taken from the user itself. N equals to input, enter the length of circular convolution sequence. Now this is the first for loop, which is for m. Okay, so m equals to 0 colon n minus 1 will generate a vector with the step size of 1 from 0 to n minus 1, where n is the length of the circular convolution that we need to calculate. Then we'll initialize xc variable to 0 with argument of m plus 1. Now why is this m plus 1? I'll come to a point. Then the inner for loop for k equals to 0 colon n minus 1. Now this is the indice, or this is the index over the summation. Okay, to get the different iterations, we'll be using this for loop, and this is the formula that we have implemented. So x1 is the first sequence, x2 is the second sequence. We'll multiply them together and we'll keep on accumulating its partial product, and that result will be stored back in the variable xc itself. We'll end both the for loops. Z equals to disp of x will display the content that is stored in xc. For plotting, we'll describe one more index, n equals to 0 to n minus 1. We'll divide the graph field into 3 rows. In the first row, we'll be plotting the first sequence, x1. In the second row, we'll be plotting the second sequence, x2. And in the third row, we'll be plotting the circular convolution output with their respective x labels and y labels. Now how exactly this part of the code works, we'll work it out manually, then you can understand it better. Okay, we'll solve this same problem but by using the code that I have written. Okay, and one thing to understand in Octave is always the starting point of a sequence or the starting index of the sequence in Octave is 1, not 0. For our reference it is 0, but origin of 0 or the starting index of the 0 for a sequence will not be identified by the discrete system computer. So it will always start from 1. So I have written two sequences here. X1 of n equals to 2 1 2 1, x2 of n equals to 1 2 3 4, and above that I have written their respective index places. Okay, so it is not starting from 0, it will be starting from 1. 1 2 3 4, 1 2 3 4 are the indices of these samples. I have rewritten the code for m equals to 0 colon n minus 1. N minus 1 value will be 3. Will initialize the xc to 0. Now this m plus 1 is because we are generating a vector starting from 0, but 0 index will not be identified by the octave. So we'll add 1 to it to make it as xc of 1, which will be the starting index in the octave environment. Then the second for loop for k equals to 0 colon n minus 1, n minus 1 will be 3 again, and this is the actual formula which computes the circular convolution. Xc of m plus 1 equals to xc of m plus 1. So whatever result we calculated in this iteration will be stored back in xc itself, and it will be used as the initial value for the next iteration, plus x1, the first sequence of k plus 1. Again, the index value 0 will not be identified, so it has to be added with 1, multiplied by x2 of mod m minus k comma n plus 1. Now how this mod function works in the octave we have seen with examples in the previous labs, and again I'll be explaining them. Okay, so when the program starts executing, after taking the length of the circular convolution sequence from the user, after executing line number 4, the execution starts from line number 5. So first iteration over m will be taken. So for m equals to 0, next line will be executed. Xc of 1, m is 0, 0 plus 1, 1 will be initialized to 0. Now xc of 1 is the first point in the circular convolution. Next for loop will be executed for k equals to 0, first value, first iteration. Now both m and k are having 4 iterations to carry out. So in the first iteration they'll be verified for m equals to 0 and k equals to 0. Now for k equals to 0, immediately next line will execute, that is m is 0, xc of 1 equals to xc of 1 plus x1 of k plus 1. K is 0 for this iteration, 0 plus 1 will be 1. X2 of mod of m minus k. M is also 0, k is also 0, so 0 comma capital N. Capital N is 4 plus 1. Now how does this statement evaluated? Mod of 0 comma 4. Now mod of 0 comma 4, when both the arguments are positive, the result will be a itself. Now the general notation for modulus value is, you can type help mod in the command window. It will give you the documentation regarding that. Mod of x comma y, it will be having two arguments. It will compute the modulo of x and y, okay, by using this formula. Okay, and apart from that, this function, mod function, handles negative values correctly. That is, mod of minus 1 comma 3 is 2. It will not be minus 1. But when both of these are positive, when x and y are positive, output of mod x comma y will be x itself. Okay, so mod of 0 comma 4 both are positive, so mod of 0 comma 4's value will be 0. 0 plus 1, 1. X2 of 1, x2 of 1 represents the first sample in the second sequence, whose value is also 1. X of 1, x of 1 is the first sample in the first sequence, whose value is 2. So 2 into 1, and xc of 1 was initialized to 0, so it is 0. 0 plus 2 into 1, 2. Now this time 2 will be stored in xc of 1, or xc of 1 will be updated to 2. The value of xc of 1 will be updated to 2. Once this line is executed, once this line is executed, line number 8 is executed, all the iterations on k is not over. Only first iteration on k we have computed. We have three more iterations to do. So it will go back to line number 7. The execution will go back to line number 7 and it will take the second iteration on k, that is for k equals to 1. And the next line, formula line, will be executed again. Now with k equals to 1 this time. So xc of 1 equals to xc of 1 because xc index is m. M is still 0 for this iteration. Xc of 1 equals to xc of 1 plus x1 of k plus 1. K is 1 this time. So 1 plus 1, 2. And x2 of mod m minus k. M is 0, k is 1. So it will be mod of minus 1 comma 4 plus 1. Mod of minus 1 comma 4 will be 3. 3 plus 1, 4. X2 of 4. X2 of 4 is the fourth sample in the second sequence with amplitude 4. So x2 of 4 will be 4. X2 of 1 is the second sample in the first sequence, which is 1, and it will be added to xc of 1. Now from the previous iteration, xc of 1's value is 2 now. So it will be 2 plus 1 into 4, which will be equals to 6. And after this iteration, xc of 1's value will be updated to 6. So again, the inner for loop will be incremented once for k equals to 2. This will be redone. Xc of 1 equals to xc of 1 plus x1 of 3 multiplied by x2 of mod m minus k. M is 0, k is 2, so it will be minus 2 comma 4 plus 1. Mod of minus 2 comma 4 is 2. 2 plus 1, 3. X2 of 3, whose amplitude is also 3, and x1 of 3 is the third sample in the first sequence, whose amplitude is 2. 2 into 3, 6. 6 plus 6. Now this 6 is from the previous iterations output, whose result will be 12, and xc of 1 will be updated to 12 now. And for the last iteration on the inner for loop for k equals to 3, we'll redo it for the last time to obtain the first point in the circular convolution. Xc of 1 equals to xc of 1 plus x1 of 4, because k is 3, 3 plus 1, 4. X2 of mod of minus 3, m minus k. M is 0, k is 3, so minus 3 comma 4 plus 1. Mod of minus 3 comma 4's result will be 1. 1 plus 1, 2. X2 of 2, x2 of 2's value is 2, and x1 of 4's value is 1, and the previous result that was stored in xc of 1 was 12. So 12 plus 1 into 2 will be 14. Now after k equals to 3, so all the iterations in the inner for loop has been completed. So after executing k equals to 3, after 8th line, it will end the inner for loop. This part is over now for one value of m. Now the control will go back to 5th line. Now this time m will be incremented by 1. So for m equals to 1, xc of m plus 1. M is 1 this time. So 1 plus 1 will be 2. This will be the second circular convolution point, and all the other iterations of k will start from 0 again. So for k equals to 0, xc of 2 equals to xc of 2 plus x1 of 1 multiplied by x2 of mod of 1 comma 4 plus 1. Mod of 1 comma 4's result will be 1. 1 plus 1 will be 2. X2 of 2 will be 2, and x1 of 2 is x1 of 1 is 2. 2 into 2, 4, and xc of 2 is initialized to 0, so 4 will be stored in xc of 2, and this continues for m equals to 1. After completing all the iterations on k, m will be incremented again for m equals to 2, and the same thing repeats till m equals to 3. At the end, we'll obtain the circular convolution result 14, 16, 14, and 16. Okay. Now, all of this will be done internally in the octave. Just to show how this works, I have solved that here. You all try this. Okay. So when you execute this program, To execute this program, click on run button, go to command window. You will be asked to enter the sequences. So first sequence in our example is 2 1 2 1. Okay, second sequence in our example is 1 2 3 4, and the length of circular convolution, both are 2.4 point sequences, so I will be calculating 4 point circular convolution out of these two. Press enter, will get the result. So the result has been verified. The circular convolution between these two sequences is 1416 1416. This is the numerical result. The same thing we have plotted here. There are three rows. In the first row we are plotting the first sequence with sample values 2 1 2 and 1, and in the second row we are plotting the second sequence with sample values 1 2 3 4, and this is the output which has been plotted in the third row, 14 16 14 and 16. So this is how we implement circular convolution by using direct method in the Octave environment. Now coming to the second program. In this program we'll implement circular convolution by using DFT and IDFT method. Okay, now here, unlike linear convolution, the length of the circular convolution is not fixed. Okay, length of the circular linear convolution will be length of the input plus length of the impulse response minus 1. Now like that, length of the circular convolution for any system is not predefined. So if we have two 4 point sequences, I can calculate 8 point circular convolution from those 2 point sequences, or if we have two 4 point sequences, I can calculate 2 point circular convolution from those. So we'll use nested if else statement to check the length and then calculate the circular convolution appropriately. So first the basic line, next we'll ask the user for two sequences, x equals to input enter the first sequence, h equals to input enter the second sequence. Now NA will be the length of x, NB will be the length of the second sequence h. Okay, now we'll compare these two. If NA is equal to NB, that is if the length of both the sequences are same, then we do not have to do anything. M equals to x will assign x and h, the first sequence and second sequence, to the new set of variables m and n. If this condition is true, if this value is true, then else if and else will not be executed. Directly end will be executed. So it will come out of the loop. Control will come out of the loop and line number 17 and 18 will be executed. In line number 17, we'll calculate the n point DFT of the m. M is nothing but first sequence itself if the length of both the sequences are same. So x equals to FFT of m. This will calculate DFT, n point DFT of the first sequence. H will calculate n point DFT of the second sequence. Then we'll multiply those together. We'll multiply the n point DFTs of both the sequences and take IDFT by using IFFT function available from the Octave. Small y equals to IFFT of capital Y, because in capital Y we have stored the product DFT, and then whatever sequence we obtain from this inverse discrete Fourier transform, it will be stored in small y and will plot it stem of y. Now this will be the condition if the length of both the sequences are same. If length of the first sequence is more than length of the second sequence, say length of the first sequence or the number of samples in the first sequence is 4 and number of samples in the second sequence is 2, okay, then first sequence will be as it is, will retain the. Now this if condition fails, if NA equals to NB, this will be false now, so the program control will come to else if. Now it will check it, is NA greater than NB? Yes, this becomes true. So the lines within this else if will be executed. In that, we'll assign x the first sequence to m, and the second sequence will be zero padded to make its length equal to the length of the first sequence. So n equals to h. All the samples from the second sample sequence will be retained as it is, and zeros, appropriate number of zeros will be padded. Zeros of 1 comma na minus nb, the difference between the length of two sequences, and that new zero padded sequence will be stored in n. Next, once this is true, the program control will come out, and again the DFTs of zero padded sequences will be calculated. X FFT of m, h FFT of n, y equals to the product DFT and their IDFT, and it will be plotted. If length of the second sequence is bigger compared to the length of the first sequence, then if and else if both will fail. So else part of this nested else if will be executed. When this becomes true, the first sequence will be zero padded and second sequence will be retained as it is. And next, the endpoint DFT of both those sequences will be computed, and then its IDFT will be taken. Now let us verify this for all three possible conditions. But first, we'll take the two sequences that we considered as an example. Enter the first sequence, two 4-point sequences with sample values 2121 and 1 2 3 and 4. So this time the length of the first sequence is 4, length of the second sequence is also 4. So if condition will be true, so directly their n-point DFTs will be calculated. You can see here, first sequence 2121 is assigned to m, second sequence 1234 is assigned to n. Capital X is the endpoint DFT of m. So capital X 6020 is 4-point DFT of 2121, and capital H 10 minus 2 plus 2j minus 2 minus 2 minus 2j is the 4-point DFT of the second sequence, that is 1234. Capital Y is product between these two, 10 into 6 60, 0 into minus 2 plus 2j 0, and so on. Capital Y is the product DFT and small y is its 4-point IDFT. 4-point IDFT, which should be the circular convolution between these two sequences, and we are getting the correct result. It is 1416 1416, and it has been represented graphically here. So this is just the convolution output with sample values 14 16 14 and 16. Now let us execute this program for different lengths of first and second sequence. Now let us consider first sequence to be of 4.1234, second sequence to be of 2 point. Okay, so there are 4 samples in the first sequence and 2 samples in the second sequence. When you press enter, NA is 4, NB is 2, so NA is greater than NB. Else if part will be executed. In the else if part, first sequence will be assigned as it is to M, second sequence will be zero padded. First two samples 1 and 2 are retained, and 2 zeros are to be padded to this to make its length equal to 4. And then capital X is the 4-point DFT of the M, capital H is 4-point DFT of N, their product DFT and their IDFT 9 4 7 and 10. So this is the circular convolution, 4-point circular convolution between these two sequences. And likewise for the last case, this time we'll take 2-point first sequence 1 and 2 and 4-point second sequence 1 2 3 and 4. So first sequence will be zero padded, second sequence will be retained as it is, their respective 4-point DFTs, product DFT, and their respective IDFT with sample values 9 4 7 and 10, and this is the graphical result. So we have implemented the circular convolution by using DFT and IDFT method, which checks the length of both the sequences, and then accordingly it will calculate the circular convolution between those two sequences. So these two programs, they implement the circular convolution between two sequences. Now we'll understand the properties of convolution. Now these properties we have formally studied them in the previous semester. While studying signals and systems in module 2, we understood for convolution summation and for convolution integral as well. So we did prove all these three properties: commutative property, associative property, and distributive property. So here we'll just go through the statement and what exactly it means. Okay, and then we'll write the program to verify that. So commutative property says that input convolved with the impulse response will be same as that like impulse response being convolved with the input. Both mean the same thing. Okay, so in terms of a linear time invariant system, if h of n is the impulse response of this LTI system and x of n is the input to it, you can interchange both of these, impulse response and the input. It will result the output of this linear time invariant system will be same. It doesn't matter. That's what commutative property mean. And associative property states that x convolution with h1, this entire convolution is convolved with h2, has to be equals to x convolution with convolution between h1 and h2. Now if we have two linear time invariant systems with their respective impulse responses as h1 and h2, and if we have an input x of n to it, then the output of first linear time invariant system will be z of n. Now this will be the convolution between the input and the impulse response h1, which will be applied as an input to the second linear time invariant system whose impulse response is h2. Therefore the total output will be x of n convolution with h1 of n, which is in turn convolved with h2 of n, the left hand side of this associative property. Now what it means is, instead of having two different linear time invariant systems, I can have just one linear time invariant system, and its impulse response will be convolution between the individual impulse responses. So x of n convolution between h1 convolved with h2. This will be the right hand side of the associative property statement. And lastly, the distributive property. Now this is the parallel arrangement of linear time invariant systems. If both these linear time invariant systems share the common input, then their output of the first linear time invariant system will be convolution between the input and the its impulse response, that is x of n convolved with h1, and the output of second linear time invariant system will be convolution between the input and the second impulse response, and the total sum of this system will be x1 of n convolution with h1 plus x of n convolution with h2, which is the right hand side of this distributive property. Or else we can have a single linear time invariant system whose impulse response will be sum of the individual impulse responses h1 plus h2, x of n convolution with h1 plus h2, which will give us the right hand. Both all of these arrangements in terms of commutative, associative, and distributive property will result into will give us the same results. So in octave program, the first commutative property is implemented. We'll be using a built-in function available that we have studied in the previous lab to obtain the convolution. So we'll take two inputs from the user. We'll compute convolution between them in the different arrangement. Y1 is convolution between x and h, and y2 is convolution between h and x. Now we'll compare these two results. If y1 and y2 are same, then display commutative property is satisfied, else display invalid result, and then we'll display their respective results. When you execute this, you will be popped up to input two sequences. I'll input two sequences 1 2 3 4, and the second sequence will be of different length, 1 2 3, 1 2 3. So when you execute this, this will be the output. Length of the circular convolution is length of the first sequence plus length of the second sequence minus 1. 4 plus 3 minus 1, 6. So for both the statements y1 and y2, we have 6 number of samples and all the sample values are same, 1 4 10 16 17 and 12. So commutative property is satisfied. Now associative property. Now for associative property, we'll be requiring 3 sequences. We'll take them from the user, and then in the different combination to satisfy the property statement, this property statement will use the convolution function. Y1 will be convolution between x and h1, x and h1, this part, which will be convolved. Y1 will be convolved with h2, which will give us the left hand side. So y2 will give us the left hand side. Y3 is convolution between the two impulse responses, which will be stored in y3 and it will be convolved with x, so which will give us the right hand side. Now we'll compare these two. If y2 is equal to y4, then associative property is satisfied, else it is invalid, and then we'll display its result. So we'll have to enter 3 sequences, 1 2 3 4. Next 1 2 3. In the third sequence, let's take off 2 point length, 1 2. When you press enter, according to these statements from 5 to 8, convolution will be computed and the results will be compared. So 6 1 6 18 36 49 46 24. LHS is equal to RHS, so associative property is satisfied. And likewise for distributive property as well, we need to have the sum of two convolutions. So we'll be taking two sequences and we'll be adding them bitwise to obtain one sequence h, and then we'll perform convolution. Y1 will be convolution of x comma h, this will be 1, and y2 will be equals to convolution between x and h1, y3 will be between x and h2, and then we'll add these two convolutions to obtain y. We'll compare y1 and y now. If they are same, then distributive property will be satisfied, else it will be invalid. So when you execute this, again we'll have to give 3 inputs. Now the length of these 3 sequences, they can be same or they can be different, it doesn't matter. Okay, in this case when you add, it has to be same. So 1 2 3 4, 2 3 4 5 and 5 6 7 8. So this will be the output, because we are performing bitwise addition. In this case they are to be same, 7 23 50 90 95 83 and 52. LHS is equal to RHS, so distributive property is satisfied. So this was the today's lab, where we implemented circular convolution and verified the commutative, associative and distributive property of the convolution. If you have any doubts, you can contact me. Thank you all.